Hello, my name is Christopher Haines from the Universidad de Atacama, and today I would like to talk about the IPERS Redshift survey and how it can be used to track the evolution of galaxy populations over the last 8 billion years. Galaxies in the present-day universe can be broadly split into two main families. The top left panel shows the U-R color of galaxies from the Slow and Digital Sky survey versus their stellar mass. There is one group of galaxies with U-R colors of around 1.2, placing them in the blue cloud, and a second group with U-R colors of 2.5 to 3, placing them along the red sequence. There are a few galaxies with intermediate colors, producing what is known as the Green Valley. Splitting galaxies according to their galaxy zoo morphological classification, we see in the top right panel that the red sequence is formed by early type galaxies, while the bottom right panel shows how the blue cloud is made up from spirals. Green Valley galaxies are thought to be transitioning from the blue cloud to the red sequence. Looking at the late type galaxies alone, it seems that the blue cloud runs parallel to the Green Valley at lower masses, and then at a log mass of around 10.5 it bends upwards, pushing through the Green Valley and onto the red sequence. From this figure it seems that once late type galaxies reach a certain stellar mass, their star formation is quenched in a process termed by Peng et al. As mass quenching. This process looks capable of forming the intermediate mass early types, but the red sequence extends to much higher masses than the late type sequence. This led to the idea that the most massive early types are produced through dry mergers. However, we have to remember that we are only looking at present-day galaxy populations here. One alternative scenario is that in the distant past, the late type sequence extended to higher masses than today, but then these massive late types all move onto the red sequence before the present day. This motivates Sloan-like surveys of galaxies in the early universe to see when and how the bimodal galaxy distribution has developed and how the two sequences have evolved since a redshift of 1. With this in mind, IPERS, the VMOS Public Extragalactic Redshift Survey, was developed as an ESO public spectroscopic survey with the aim of obtaining 100,000 galaxies at redshifts between 0.5 and 1.2 using 440 hours of VMOS time on the VLT. The low-resolution red GRISM was used, giving a resolution of 220 over wavelengths between 5,500 and 9,500 angstroms. Galaxies brighter than I of 22.5 were targeted, and a simple UGOI color cut used to exclude sources with redshifts below 0.5. In total, 97,414 spectra were obtained, and the D4000 index measured for each galaxy with reliable redshift, along with their O2 fluxes. IPERS covered 24 square degrees across two fields, W1 and W4 of the Canada France Legacy Survey. Only a single pass was carried out and slits placed on 47% of targets. PSF-convolved Sursich profile models were fitted to the I-band emission from each galaxy, giving their sizes and Sursich indices, while stellar masses were estimated from SED fitting to their UGIZ-K photometry. The large volume covered, comparable to the 2DF, its 100K sample size, and the availability of D4000 indices, structural parameters and stellar masses for each galaxy enables Sloan-like analyses of galaxy populations extending back to a redshift of 1. To start with, we plot the D4000 distributions of galaxies, sliced into narrow 0.2 deck wide bins of stellar mass for 4 redshift bins from Z equals 1 to the present day, combining IPERS and SDSS datasets. Each mass slice is color-coded from blue for dwarf galaxies with log mass of 9.6, through yellow for Milky Way mass galaxies, and up to red for the most massive galaxies with stellar masses above 10 to the 11. Focusing first on local galaxies from the SSDS, we see the clear bimodal distribution with the steady progression from low mass galaxies being located on the blue cloud to high mass galaxies being located on the red sequence. As we move to higher masses, the peak marking in the red sequence gets higher, steeper, and slowly moves to larger D4000 values. In between the two peaks we see a deep green valley, and the white dashed line marks the D4000 equal 1.55 limit used by Kaufman et al. To separate young and old galaxy populations. Repeating the analysis for the first IPERS redshift bin, we can see that the bimodal distribution was already fundamentally in place for galaxies at redshifts 0.5 to 0.65, with the two populations still separated by a green valley centered at the Kaufman D4000 limit of 1.55. Continuing to higher redshifts, we can now see the development of the bimodality and the build-up of the red sequence over time, starting at the high mass end. At Z of 0.9 we only see a peak marking the red sequence in the highest stellar mass bin, and as we move to lower redshifts it extends down to include more and more mass bins. Similarly, we see no green valley at Z of 0.9, but it then rapidly develops and deepens with time. Here we plot the number density of massive blue cloud galaxies as a function of redshift. These galaxies are selected as having stellar masses above 10 to the 11 solar masses and a D4000 index below 1.55. You can see that the number density of these massive star-forming galaxies drops by a factor 5 between z of 0.8 and 0.5, with no further evolution apparent from z of 0.5 to the present day, using abundances derived from Sloan data. This rapid decline between z of 0.8 and 0.5 is also seen in the earlier Z-Cosmos data, as shown by the magenta squares. But since that survey only covered a small volume, it is strongly affected by cosmic variance. The huge volume of IPERS has allowed us to obtain large samples of rare, massive star-forming galaxies at these redshifts. What happens to this population of massive star-forming galaxies that disappears between z of 0.8 and 0.5? The only possible outcome is that they are being quenched and become massive passive galaxies. This is confirmed by comparison to the number density of massive passive galaxies, shown here by the red squares, taken from Gargiulo et al. 2017. The decline in massive blue cloud galaxies is mirrored by a coeval increase in the number density of massive passive galaxies. In an attempt to understand what happens to these redshift 0.8 massive blue cloud galaxies, we model the D4000 distribution of massive galaxies with stellar masses above 10 to the 11 solar masses as the sum of two Gaussian functions for each of our redshift intervals. In the first interval, covering redshifts between 0.8 and 1, we see that the D4000 distribution is well described by the double Gaussian model as shown by the white curve. The blue cloud population is then represented by the blue shaded Gaussian function, centered at 1.36 as shown by the vertical blue dashed line, while the red sequence population is represented by the red shaded Gaussian. The fraction of galaxies in the blue Gaussian is indicated in the top left of the panel as being 0.38. The vertical white dotted line shows our previous separation of the two populations about a D4000 index of 1.55. The blue cloud Gaussian lies at D4000 less than 1.55 at these redshifts. But then as we move forward in time, we can see it move steadily to the right, that is towards larger D4000 values. Passing through the D4000 equals 1.55 barrier by redshifts 0.5 to 65, until it becomes no more than an extended low D4000 tail of the red sequence by redshift 0. Throughout this time, the fraction of galaxies in the blue cloud Gaussian does not actually evolve that much. This suggests that we aren't witnessing a large-scale quenching of massive blue cloud galaxies, but rather a steady evolution of the bulk population to higher D4000 values as their star formation rates gradually decline. The fivefold decline in the numbers of massive star-forming galaxies between z of 0.8 and 0.5 can now be understood as the blue cloud population moving as a single block through the D4000 equals 1.55 limit during this epoch. To test this further, we now plot the D4000 evolution of the blue cloud population as a function of time. The large orange points, connected by the thick shaded lines, show the observed evolution of the central D4000 value for the best fitting Gaussian to the blue cloud population, whereby it rises steadily with time from 1.36 at redshift 0.9 to 1.73 at the present day. The coloured curves instead show the D4000 evolution for a range of secular evolution models in which the star formation rate evolves smoothly as t times the exponent of minus t over tau for timescales tau from 0.6 gigayears in red to 9 gigayears in blue. We see that the observed evolution of the blue cloud galaxies can be reproduced by a secular evolution tau model with the timescale of 1.2 gigayears, which is shown by the yellow curve, throughout the critical phase from z of 0.8 to 0.5 without need for additional rapid quenching. The tau model then overestimates the D4000 evolution between 0.5 and the present day, predicting that the blue cloud galaxies join the red sequence rather than remain below it. To summarize, IPERS is an ESO large program that obtains spectra for 100,000 galaxies at redshifts between 0.5 and 1.2, with the objective of providing a representative vision of the large-scale structure of the universe and the global properties of galaxies when the universe was half its current age. All of the data is now publicly available on the following website. We show how the IPERS data enables us to track the evolution of the blue cloud and red sequence populations in the D4000 stellar mass plane over the last 8 billion years. In particular, the co-moving number density of massive blue cloud galaxies drops fivefold between a redshift of 0.8 and 0.5, mirrored by a coeval increase in the number density of massive passive galaxies. This appears to be simply due to the steady decline in star formation among all massive blue cloud galaxies, rather than a widespread quenching phase at redshift 0.7. Further details can be found in the following papers. Thank you for listening.